Hey, everyone. Welcome. I'm Robert, one of the creators of Ray and one of the co-founders of Anyscale. And thank you all so much for being here. This is our very first New York Ray event, so I'm super excited to be with you all here. So most of what I want to talk about is future-looking. What are the biggest, most important trends happening in AI right now? And what are the implications for AI infrastructure? But I want to start, we've been working on Ray for a number of years now. So I want to start by sharing a little bit about the journey to get here and what that process has been like. So we started Ray in 2016 at UC Berkeley. Philip and I were doing PhDs in machine learning. And our focus at the time was trying to design algorithms for reinforcement learning, deep learning training, optimization algorithms, these types of things. And even though our intention was to spend our time focusing on the theory, on the algorithms, AI is just so computationally intensive that we ended up spending all of our time scaling things, all of our time on the software engineering to manage clusters and shuffle data and get stuff to run on GPUs, these types of things. And this seemed like a major bottleneck in AI research. And so we decided about halfway through the PhD program to start working on systems for machine learning. And we thought we had an approach that would enable machine learning people who know Python, to run their workloads across clusters of machines in a scalable way. And so going way back, this is no need to read the actual code, but I took a screenshot from one of the very first presentations we gave on Ray. This was a talk at one of the Databricks conferences. And the core idea from the very start, Ray just had two simple primitives: the ability to take Python functions and Python classes and kind of run those in the distributed setting in a scalable manner. And if you fast forward to today, I think those core primitives, the idea of having a small number of very flexible primitives for distributed computing, have really stood the test of time and have enabled Ray to move beyond just scaling Python applications to really giving rise to an ecosystem of scalable libraries. Now people use Ray for training, for serving, for reinforcement learning, data processing, and there are a whole host of third-party products and libraries built on top of Ray for post-training, for multimodal data processing, for LLM inference, and beyond. But this is where we got started. Now, it did take a little bit of time for Ray to get to where it is today. And when we started Anyscale in 2019 to commercialize Ray and to continue developing Ray, there was only one serious production Ray user at the time. That was Ant Group. So it's a Chinese company that makes Alipay. And they're a power user today of Ray. They actually run about a third of their compute with Ray. But at the time, they started using Ray and invested in Ray when no one else was using Ray. And so they were the early adopter. Then over the next couple of years, Uber adopted Ray for training all of their models. And then Pinterest was one of the next major Ray users. And so Ray adoption was slowly growing. But these were really early adopters. And at the time, the market for distributed computing for AI didn't really exist. So the inflection point for Ray and for the market overall was generative AI. Right? With the rise of generative AI, with the release of ChatGPT, that was the point at which AI became relevant for nearly every business, and the need for scale became far more obvious. That was the point at which it was clear you have bigger models, you have more data, people are talking about scaling laws, you need a lot of GPUs, things like that. And that was when Ray adoption really started to take off. And you'll hear from some of these companies today, from folks at 2 Sigma, Bridgewater, Spotify, Nubank, many others, about how AI has impacted their businesses, what they've been building, how they're using Ray. But one of the most exciting things about working on Ray is that I really come across new use cases just all the time. I learned recently that Tencent, which makes WeChat, is using Ray to deploy all of their models for WeChat. It's a massive deployment. That includes, of course, content recommendations, ranking, content generation, tons of short-form video processing. I learned that DeepSeek is using Ray. I learned that XAI is using Ray. So there's really new things like this every week. So generative AI was the inflection point for where, and really what brought Ray to where it is today. But AI, we're at a moment in time where AI is changing incredibly quickly. So I want to talk a little bit about some of the most important trends and developments that we see in AI today, and then what that means for AI infrastructure. So the first trend I want to talk about is what I'll call AI data processing. This is, I think the nature of data processing is changing in a fairly dramatic way. And there are a few different reasons for this. So the first is this shift from tabular data to multimodal data. And this is not about tabular data going anywhere. This is about the rise of multimodal data. And with multimodal, I'm talking about video, images, and so forth. Now, most companies have a lot of data. And the reason they have all of this data is they want to get insights from the data. They want to get value from the data. And the dominant paradigm for getting value and getting insights out of data today is to run SQL queries on your data, or simple analytics. And that works great if your data is nicely structured in a table or in a database. Then you can run your analytics. But if your data is a video or a PDF or a screenshot, you're probably not running a SQL query on that. So what do you do? Well, historically, we haven't done very much. Most companies haven't done very much with that type of data. And as a consequence, if you're not getting much value out of that type of data, you're not going to collect as much of it. But what's changing now is that machine learning models are becoming more powerful. You now have models that can watch a video and answer questions about it, or models that can read a PDF or read a document and analyze it, right? And so as models become powerful enough to really work with all different types of data, we're going to start getting value from all different types of data, and we're going to start storing and collecting way more of these types of data. And as more data becomes just different data types, multimodal, what you're going to see is that the way we work with this type of data is not by just doing normal analytics and normal processing, but really we work with this data by running inference. Right? The way you work with this type of data is by feeding it through machine learning models. And so data processing is becoming very inference heavy. Okay? That could be something as simple as an embedding model to later search and retrieve. Or it could be a video understanding model. It could be all different types of models. But that is a big trend we're seeing, that data processing is becoming very inference heavy. And it's not replacing regular processing. You still need to do all of the usual data transformations. It's a growth area. And of course, inference if you think about regular transformations, all the big data processing systems out there, Spark, Flink, Hadoop, and so forth, they were built for CPUs. But inference runs on GPUs. So data processing is shifting to be a CPU plus GPU workload. Right? And if you think about this from an infrastructure perspective, that's a pretty big shift. This is a very underserved area when it comes to existing systems. And this is an area where we've seen tremendous growth with Ray. And if I were to summarize all of this in kind of one phrase, I would say that we're going to be getting more value than ever from data. We're going to be able to work with more types of data than ever. But the dominant paradigm for working with data and getting value from data is going to shift from being about SQL on CPUs to being about AI on GPUs, or inference on GPUs. So that's the first trend. This is something we've been very excited about at Anyscale. The second thing I want to talk about is agentic AI. Now, when we build AI applications, the nature of the AI applications that people are designing today, that people are starting to develop and to ship, is changing. Most applications in the past, machine learning applications, have a single model behind some endpoint somewhere. Now we're starting to see much more ambitious applications that involve compound AI systems, that involve many models composed dynamically together with a ton of different application logic in the mix. And these types of applications can be far more powerful. They can automate far more complex workflows or tasks. But they are also far more complex, both to design and to deploy. So on the architecture side, to actually design these applications, and I know the text is not readable here, but there are many different decisions you have to make when designing these architectures, from the which models to use, to how to prompt the models, to how to manage context, how to do retrieval, how to rank the context, how to chunk the data, how to do all of these types of things. Right? There's a number of different decisions you have to make here, and you're going to have to run experiments. You're going to have to try many different decisions, and you're going to have to update these decisions as you go and as new models are released. And once you've made all of these decisions and you're actually getting around to deploying the thing, it's not just one model. You're combining API calls with open models, with smaller, specialized custom models. And some of these models might be small and run on a fraction of a GPU. Others might be large and span many GPUs. Right? Some are going to be very quick to invoke and run. Others are going to reason for long periods of time. And so there's tremendous heterogeneity. And these models have to auto-scale. Just the deployment complexity around running and managing these applications is growing. And these are the types of use cases where, as serving workloads, as a consequence of agentic applications, serving workloads are becoming much more complex. And this is exactly why companies like Tencent are using Ray for deploying all of their models for WeChat. This is serving complexity is growing far more complex. So the third trend I want to talk about is post-training. You may be familiar with the pre-training, post-training distinction. So pre-training is about getting a model to absorb lots of general world knowledge. And post-training is about teaching that model getting it to learn some new capability like reasoning, or some new skill like coding, or performing some enterprise workflow. And this is a relatively new area. It represents, the amount of compute used for post-training today is relatively small compared with pre-training, but it's growing rapidly. And this is going to be a huge growth area. And this is also the part that's really relevant for a lot of businesses, because it's about adapting the model to get really good at certain tasks. And you might think, OK, pre-training, post-training, they're both just training. So what's the difference? Well, they actually have entirely different tech stacks. And why is that? Well, post-training has a lot more moving parts. It's a lot more complex. Here's a figure from a blog post from folks at UC Berkeley. And if you look at the pink box, the part that says learning algorithm, that is shared. That's the same as pre-training, right? That's the part where you have the model, you load the data, and you update the model, compute gradients, and update the model weights. So that part is common. But everything else is different. So with post-training, a lot of post-training is done through reinforcement learning. You're still doing training, but then you're taking the model that you're learning, and you are using it to actually generate new data that you're then going to train on. And how does that data generation part work? Well, say you're trying to teach the model to get good at coding, software engineering. Well, then the model is actually being used to take actions in some environment. So you may have a software environment running in a Docker container, and the model is suggesting things like clone this Git repository, apply this patch, run this test suite. And that's actually being executed in a loop with the software environment. And then all of that sort of execution trace of what's happening might be sent to another model, like a reward model, which is scoring the entire thing and deciding how well it did. And then all of that reward and the execution trace are being sent back to the training part to update the model, right? And so you have the training part, you have inference to actually generate from, do inference with the model. You have a bunch of simulations you might be running in other containers, and you're shuffling weights back and forth, execution traces, and all sorts of things like that, right? And all of this could be happening in the presence of failure. You need to autoscale the different pieces independently. They might use different hardware resources. So there's a lot of complexity here, but also a lot of potential. This is something we've been really excited about with Ray because all of the major open source post-training frameworks have been built on top of Ray. So there's ByteDance released one called Virl, which is super popular. NVIDIA released one just, I think, a few days ago called NemoRL, which uses Ray. There's one called OpenRLHF. There's one called OpenInstruct. There's one from UC Berkeley. So there are a ton of these things. It's very early days with post-training, right? There's a lot of fragmentation. There's going to be a lot more frameworks built in the coming years. But this is, I think, a super important trend. OK, so I talked about a few different emerging workloads and use cases that we're really excited about, that I'm really excited about. Now I want to talk a little bit about what that means for the AI infrastructure, the tech stack. And when we talk with a lot of companies, a lot of machine learning platform teams, a lot of them are asking themselves, how do we support these workloads? Like going forward, how do we make sure we can take advantage of the absolute latest capabilities? And we all know that under the hood, this is powered by GPUs, by hardware accelerators, right? GPUs are central to all of the progress and everything we've seen in AI. But I've drawn this diagram in kind of a leading way, right? Because I'm trying to imply that there's a big missing component between that needs to be there to connect the applications to the hardware. And many of the ML platform teams, many of you here are probably working on that software stack. So it's early days here. We've worked with a lot of different companies that build out this stack in different ways. And I think we're at a period where you see a lot of fragmentation, a lot of different technologies emerging. But we're also starting to see a lot of common patterns in how these tech stacks are built. So I want to share some of the layers that I see emerging here and how common patterns that we see from a lot of different companies. Okay, this will be an oversimplified picture, but I think it captures some important trends. So, and just to give you an example, this is a lot of companies have blogged and written extensively about their software stacks. No need to read the actual boxes. This is from a blog post by Roblox talking about their basically how they built their AI infrastructure. And the point is just that there are a lot of moving parts. There is a lot of complexity, and there are a lot of pieces that go into this. But we've also, a lot of what I'm going to say is informed by stuff we've seen from Pinterest, from Uber, and just many of the Ray users that we work with. So, OK, so the first layer I want to talk about is the training and inference frameworks. So think about the ecosystems around PyTorch and JAX. And the centerpiece of this, well, the key responsibility of this layer is about running the model efficiently on the GPU. It's about interfacing with the GPU. And this is all centered on a deep learning framework. PyTorch is dominant at this layer. JAX is also super popular, especially for running on TPUs. There used to be a ton of different frameworks here, right? I was at Berkeley. People created Caffe. There's Theano, MXNet, many other options. But really, this has been PyTorch has emerged as a winner here. But it's not just PyTorch. There are higher level frameworks for model parallelism on top of PyTorch. So models are getting bigger. And so the role or the need to shard these models across multiple chips is growing. And PyTorch FSDP, DeepSpeed are two of the most popular frameworks for doing this. But one interesting, and they're general. When I say general, I mean they apply to any model. One interesting recent trend has been the emergence of transformer-specific frameworks. And so transformers, this is the model architecture for large language models. They are important enough and kind of unique enough that they deserve their own class of frameworks and optimizations. VLLM, SGLang, TensorRT-LLM are examples of inference engines for transformers. Megatron is for training. And the kinds of custom optimizations you need for transformers, there's a ton of them. It's things like page detention, speculative decoding, chunked prefill, continuous batching. There are many transformer-specific optimizations. So these frameworks are relatively new, but have become super popular over the past couple of years. All right, so again, the responsibility at this layer is about running the model, the single model performance on the GPU. Okay, so the next layer under this is the distributed compute engine. This is what we're working on with Ray. And this is, if PyTorch is about single model performance on the GPU, Ray is about solving distributed systems challenges for scaling. Right? This is things like task scheduling and execution, things like data ingest and movement, things like failure detection and handling. Okay? So solving the core systems challenges that happen when you need to scale. And if you think about back to the post-training figure that I showed, PyTorch, of course, is being used for inference. It's being used for, and along with VLLM, PyTorch and perhaps Megatron or FSDP are being used for the training part. And Ray is orchestrating all the different processes, moving the data around, handling auto-scaling, handling failures, things like that. OK, so that is this distributed compute layer. And it's very complementary with the deep learning or the inference and training frameworks. So the next layer below is this container orchestration. This is about provisioning. The responsibility at this layer is about provisioning compute, right? Interfacing with the cloud provider to provide compute. It also handles, it's responsible for workload and user multi-tenancy. So scheduling at a much coarser level. Right? If Ray is saying, here's my training job, within my training job, I'm going to run this task here and this task here and move data from here to here. At this level, we're saying, here's one job, here's another job. They need to share a common pool of resources. Right? So much more coarse-grained scheduling, handling workload and user multi-tenancy, managing container creation and the lifecycle of containers, and provisioning compute. Right? So at this layer, Kubernetes is dominant. Slurm is super popular among researchers. And you can think about, of course, Kubernetes was created for microservices and biases a little toward online workloads, but of course can do both. Slurm's strength is really in offline and batch workloads. Okay, so there are many variations on this, but this is, I think, captures some of the important layers of software stacks that we tend to see. It is, there are many variations on this, and there's lots of stuff omitted from this picture. But this captures a lot of common patterns that we see from many different companies. And there are a lot of benefits. There can be a lot of benefits to adopting this type of tech stack. So we've worked with many companies here. Many companies have blogged and written about the benefits of adopting Ray and adopting these different technologies. Like Instacart has talked about being able to train on 100 times more data after adopting Ray and adopting these technologies. So why does that matter? Many companies are looking at scaling laws, trying to train on orders of magnitude more data, and this can enable that. Niantic has talked about being able to reduce the lines of code by 85%, all while increasing performance, improving cost. And Amazon has talked about migrating to Ray and actually, in the process, saving over $100 million per year. Okay, and of course, all of this is possible because of the work that the open source community has done. I'm very excited to be working on Ray with you guys, with this community, and helping build out the overall open source stack for AI infrastructure. So thank you all very much. Next, I'm going to invite David Wang up, our head of marketing, to talk about everything else that we're building here at Anyscale. So please welcome David, and thank you so much.
Thanks, Robert. Look around this room. This room is packed with enthusiasts for AI infrastructure, building next-generation applications. And what I'd love to talk to you about today is how we advance forward. Like we all know, we've heard from Robert that Ray has tremendous power. It's a very, very powerful computing framework to build AI workloads and run them at scale. I know this guy, sorry, threw me off. And so really what we're talking about here is that in order to scale Ray in production, it takes a lot of engineering investment. And our mission at Anyscale is to help developers productionize Ray applications easier and get to market faster. And so what we've seen from our experience working with hundreds of teams is that AI teams get blocked running Ray in production across 3 different phases of their lifecycle continuum. The first is getting started running their first workload, building their first cluster, getting to production. The second phase where they get blocked is running reliably in production at scale. And the third is building and empowering an organization-wide AI platform on Ray. And at each of these stages, there's an increasing level of complexity for engineering teams, but there's also an exponential increase in the amount of value that can be realized across your engineering organizations. And so for Anyscale, our mission in life is to meet you where you are within your journey across these 3 stages and to help unblock your engineering teams in one of 3 ways. The first is around developer velocity. Now, imagine for a moment that we had access to like the fastest super engine in the world, 1,000 horsepower beast that can go 0 to 60 in like 1 second. But imagine we had this engine, but we didn't have a chassis, we didn't have seats, we didn't have a steering wheel, and we didn't have any wheels. We probably couldn't get very far very quickly. And the same can be said for Ray. Because for any of you that have run Ray in production, you'll know there's quite a bit of work that's required in order to actually stand up the environment. From building containers, configuring clusters, managing dependencies, orchestrating jobs, waiting for cold starts from new nodes, and debugging jobs. It's quite a lot. And so the reality is you have Ray as a great framework, but you have to build out all of this tooling around Ray in order to make it productive for your developers and your teams. And this is a lot of work and effort of tooling that's required to stand up. Tooling that has to be integrated, tooling that has to be developed, tooling that has to be maintained, so forth and so forth. And so really where Anyscale comes in is that Anyscale provides a great developer experience right out of the box. We package in all of this tooling, it's built into our control plane, and we make it available for you and your teams to be able to accelerate your projects. And this really comes down to empowering you guys with workspaces so your developers can easily launch jobs, run those jobs in production, iterate as fast as you can. And so with that, I'd love to show you a glimpse of the power of the Anyscale platform through a very short demo. So first, what you're going to see is the ability for us to be able to show you how to build and scale workloads in production using Ray. You're going to show an environment. It's a data processing workload. We're going to start first with opening a new workspace. As we fill out the initial parameters of the workspace, you'll see the ability to auto-select nodes. This is about enabling auto-scaling, so you're not having to mess around with the infrastructure as you want to scale up or scale down. We'll then go over to the code, and we'll add in our code to run our first job. As we add in the VS Code, you'll see us run the job and see that a dependency is missing that's preventing the job from being executed. No fear, we'll head over to the Dependencies tab. And when you go in the Dependencies tab, you can see how easy it is to update your dependencies. And in the background, we're actually executing and updating the dependencies across all the nodes in the environment, all under the hood without having to do any node restarts or reboots. And now we rerun the code, and you're going to see that the code is now executing as it's supposed to. If you look on the far right corner as well, you're going to see that we enabled auto-scaling. And with auto-scaling enabled, we can actually run this environment at scale, scale up, scale down as you need without any ops support. Last but not least, we'll head over to the Metrics tab. And here we're able to see all of the different observability metrics for your workload as well as your resources, which helps with resource management, workload optimization, performance improving, etc. And so within this short 30-second demo, you can have now like a quick glimpse to see what is the power of Anyscale for your Ray environments to make it really easy to build and scale your workloads in production. Now, Anyscale's value for Ray is more than just a great developer experience. Because at the end of the day, what your teams are responsible for is ensuring that your workloads run reliably in production as well. And so production resilience plays a really important part. Because the last thing you want is your batch workload or your serving workload to fail in production. But the reality is, as we all know, failures are inevitable. We're dealing with distributed systems. And so for anybody here that's ever run Ray in production, you've likely faced one of these failures somewhere across the entire infrastructure stack, right? You might have dealt with issues like performance out of memory. You might have dealt with a spot instance was preempted by a cloud provider. Maybe you had a failed GPU. Maybe you had a noisy neighbor resource contingent issue with multiple workloads running on the same environment. Whatever the issue is, it ultimately leaves you and your teams vulnerable, but also leaves you guys dealing with P0s at all hours. Now, despite the fact that failures are inevitable, Anyscale for Ray has built in full stack production resiliency within our service. And what that means is we've taken the entire stack and we've plumbed in resiliency measures that enable the workloads to run all times. We've enabled resiliency in the control plane, integrated alerting, monitoring, logging, checkpointing for jobs, job level retries. We've also enabled resiliency at the runtime with head node HA as well as task level retries. And then finally, we enabled resiliency at the infrastructure layer with robust instant policies that allow you to be able to use spot instances at the lowest cost of computing infrastructure with automatic failback so you can ensure that your workloads run reliably without any issues of preemption getting in the way. And so all of this is really about countermeasures that enable you to run your Ray workloads in production reliably at scale. And so last but not least, many customers and users of Ray have realized incredible resource efficiencies when they're running Ray in production. Anyscale takes resource efficiency to a whole new level, which enables really, really highly efficient resource utilization, GPU utilization, that ultimately drive down the cost of running compute so you guys can do more with less. And we drive efficiency for Ray environments across 3 key dimensions. The first is around an optimized runtime for Ray, which we call Ray Turbo. The second is the use of smart instances. And the third is through optimal scheduling. When you look at the runtime, we introduced Ray Turbo about a year ago, this time at Ray Summit in San Francisco. Ray Turbo's runtime was built on the premise that there are a tremendous number of tuning levers and optimizations that are possible to improve workload performance. Ray Turbo builds in all of these optimizations directly into its libraries to make it available for our customers, which allows for a better price for performance. And the results have been staggering. What we've heard from companies using Ray Turbo is they've seen 4.5 times better data processing price for performance. And similar effects can be seen across model training and model serving as well. For the second dimension of smart instances, we know that the cost of compute is expensive. And so we want to be able to help our customers leverage the lowest cost of computing infrastructure by leveraging different types of instance types, like spot instances, as an example. Well, running spot instances in a production environment is difficult because you have the issue of cloud preemption where you might lose that instance. But what we do is we monitor the entire fleet of available resources. And by monitoring the available fleet, we're able to actually leverage fallback mechanisms so that if a spot instance gets preempted, you're going to be protected because your workload is going to stay up and running at all times. And this allows for both a resiliency value, but also the ability to leverage spot reliably, lowering your cost of compute by up to 50%. And the third dimension of cost efficiency is really about optimal scheduling through Anyscale's global resource scheduling. And this is allowing you to run multiple workload clusters. And so within these multi-cluster environments or multi-workload environments, you have the ability to have resource isolation, fair scheduling, and multi-tenancy built in. Plus, as a bonus point, the global resource scheduler also enables you to detect as well as prevent by closing off any silent phantom GPU workloads that are running idle, so you're preventing your cost bill from going up. So all of this really comes together in the fact that Anyscale completes Ray. You have a great framework, meets a great developer experience so that you and your teams can look at the value of Ray and run like your AI platforms that you want to build to empower your AI teams, but do it on a seamless dynamic pool of resources, heterogeneous environments with a high degree of efficiency. And that's really what we're all about here at Anyscale to help support our customers. But in the vein of supporting our customers, beyond even the platform, like we're here, right? We're here and present through training, support, services, so that as you and your teams are ramping up on Ray and trying to scale into org-wide AI platforms and multiple use cases, we're here to help support you along your journey. And so we love open source. We love seeing our customers successful, and so it's exciting to hear about the great success stories that our customers are having when they're running Ray in production with Anyscale. Runway, which we're going to hear later from today, drove 85% improvement in their developer velocity when they're using the AI platform. Attentive has seen tremendous cost advantages by running Ray because of the parallelization that can be provided through the efficiency of our architecture. And then Coinbase has been able to iterate rapidly and iterate on their models that allow them to build the platform that allows them to test and iterate quickly, but allow them to build better AI models faster than ever before. And so if any of this talk that Robert and I had has inspired you to look at Anyscale or has inspired you to try out Ray, we're excited to introduce to you a free trial of the Anyscale platform where you can easily log in, check out the developer workspaces, and run through 20 different application templates where we've already built in all these environments for you to check out across unstructured, multimodal data processing, to model training, to model serving, end-to-end workflows, all built out through the application templates, and you guys can try it for free. It's a great way, if you're new to Ray, to feel the power of Ray without having to stand up a cluster on your own.
Yeah.